Yeah, thank you for the introduction. Thanks for having me and inviting me for giving a tutorial here. Right, it's gonna be a bit of an experimental mode. I have like a pre-prepared whiteboard, and I'm gonna complete stuff whenever it gets technical. I'm gonna write it in so that I don't go too fast. Please interrupt me at any point of time if you have questions. I think you have to signal it in the chat, right? And the chairman will unmute you. But it's not super clear to me what the composition is between people with a physics background, with no physics background at all. I have tried to err on the side of assuming nothing, but maybe I've misjudged your pre-knowledge. So please, interrupt me at any point of time. Right, okay, so what is the topic of the set of lectures? I want to introduce what is called the stabilizer formalism, and let me try to motivate it very briefly. So quantum many-body states, as everybody knows who attended the previous tutorial, they are described by tensors, right? And in our case, we will always look at a base space C2 tensored n times, and n is some number which is typically large. So maybe 10 to the 2 to tens of millions of tensor factors that we'll be talking about. And this is a regime, of course, which is very different from the regime that maybe in algebraic geometry people look at, where often you have very few indices, maybe 3 or 4, and maybe make the base dimension larger. And the gigantic dimension of these bases, right? So the dimension is 2 to the 10 to the 7, right? So it's an unbelievably large number. This has positive and negative consequences. Yeah, and so the obvious negative consequence is that it's not practically possible to describe a generic element of such a space either analytically or numerically. Yeah, just the number of parameters is way too big. And what we have to do is we have to find then, if we want to come up with constructions, for example, in quantum computing, we have to find classes of tensors that have that can be handled, that strike a good balance between two contradictory purposes. Yeah, the classes should be small enough so that we can have a concise description. Yeah, and use a few bits, for example, to represent their elements, but also it should be large enough to capture interesting phenomenology. And there's maybe two big classes. No, one you heard about in the previous talk. These are the tensor networks, which are used in computational many-body physics. And there is another important class, which is more important in quantum computing and quantum communication. And these are called stabilizer states and stabilizer codes, right? And the construction is via involving certain matrix groups. So if you like algebra, then you're in luck today, because that's going to be the big difference maybe to what Thomas is doing about. So we are not optimizing for numerics, we are optimizing for analytical tractability. Okay, and so my presentation, my tutorial is going to have two parts. The first part, I want to introduce to you what is the problem of quantum error correction, and how does the stabilizer formalism come into play, and how can we get interesting spaces of tensors out of this algebraic description. And then there is a second part, which I don't expect I will be able to start today, but I will tell you next time. But I want to give a short teaser. And we want to apply the theory that I built up in the first part to construct a particularly cool stabilizer code, so a particular cool set of tensors. And I'm going to not explain anything here, but make a bit of advertisement for the second part. So here's the basic ingredients of this construction we are working toward in this lecture. So you start by taking some manifold M, for example, the torus. Yeah. And next step, once you have this manifold, you put a lattice on the surface, right? So you choose some number k, and you put a k by k lattice, kind of evenly spaced if you want on the torus. Now you can ask me, how big should k be? And the answer is, it doesn't really matter. As big as you can get away with, but you will see in a second, it's really going to be secondary. Right, so we have to talk about tensors. So where do tensors come in? They come in here. Now, this lattice, you can look at it as a graph, and then with every vertex, denoted here in blue, you associate a vector space, for example, a C2. So there's one copy of C2 that lives on every vertex of this triangulation of this lattice on the manifold. And then you tensor them all together, obviously. So you get a huge tensor space. And so what we will do is what the goal is of this tutorial is to construct spaces of tensors whose tensorial properties depend on the topology of the manifold M that we started with, and in some way only depend on the topology. So I think this, I don't expect anybody to understand this. It's just a teaser, but I think it drives home one point. It's not only that the regime people work in physics when they talk about tensors is very different from the regime in algebraic geometry, not only in that we are interested in tensor spaces with many more indices, but we are interested in tensors with so many indices that the actual number of indices becomes immaterial. And that the indices, they take on a life of their own, and they have their own geometry and their own topology. And the tensorial properties, in the end, they depend on the topology of the set of indices. Yeah, and so how that works, I want to get to by the end of my second lecture. Yeah. Okay. So if you think this is not cool, if you don't think this is fantastic, then there is nothing I have to offer you in life ever. So this is one of the coolest things I know. So let's try to get there. Good. I'm happy to take questions at any time, but maybe not now because I don't want to talk about this now. So interrupt me at any point except for now. Right. So this was the long-term outlook, and let's get started with the technical details. And to get started with the technical details, I want to introduce you to the problem of quantum coding. And to do this, I want to remind you, maybe, or if not, explain you for the first time, but it's very simple, the basic idea behind classical error correction and classical coding. Okay, so now we are in a completely classical setting where we have k bits, some k bit message. Let's say here the message is u, yeah, and the bits are u1 to uk, and I want to send them maybe through an undersea cable from Cologne to Los Angeles, encoding my video lecture here. And there might be some bit flips on the way, right? So the channel, the undersea cable, I don't know, there's some fish, tugging at it. And so maybe what you will receive at the other side of the Atlantic Ocean is a bit corrupted. Yeah, and now what we want to do is we want to decode this. Yeah, we want to encode the message in such a way that it's going to be resilient against a few bits flipping. And so what we do is we take some encoding procedure and map the short message to a slightly redundant message. So now it's x1 to xn, where n is the length of the message. It's longer than k, the number of bits of the message I want to transmit. And what happens in passage is that it gets corrupted. So there is some error applied to this message. And we will not get away without making some assumptions on the set of errors that occur. So let me write out the set of errors I want to consider, and they depend on some parameter. Let's call it L. And the errors are functions that map bit strings to bit strings. So let's say f2 to the n to f2 to the n, where I'm using finite field vector space notation for bit strings because I wanted to perform algebraic operations on them later. But if you're unfamiliar with this, this is just a bit string of length n. And I want to restrict the error operations in such a way that it acts non-trivially only on L bits. So it is guaranteed, this map E is guaranteed to only affect L bits. Okay, E acts on at most L less than n bits. Okay, right. So now I have received a message E of x, where up to L bits have changed, and now I want to decode. So so let's say let's think a bit, when is decoding possible, and we will do it in a very abstract way, so it's going to be easy to understand. So first we need to give a name to the set of all code words. So let C be the set of all code words, or the code. And now I want to discuss the following diagram, which is a bit of a cartoon version of what happens. So first, all the points here, these are code words. Yeah, so let's say, let's draw a dot for every code word, and let's around each code word draw a ball. and the ball should consist of all the bit strings that I can reach from X by flipping up to L bits. Yeah, and this is sometimes called the ball that has size L in Hamming weight distance. Yeah, so Hamming distance, the Hamming distance between two bit strings is just the number of places where the two differ, right? And so what we want to do is we want to take our space of messages and divide it up, yeah, and draw little Hamming weight balls around every possible code word. Okay, good. So then I get a picture like this. And so an important parameter of the code now is what is called the distance. Yeah, the distance of a code is the minimal Hamming distance between two code words. Yeah, and let's call the distance d. So here you can see, yeah, here, the distance d is introduced here. Yeah, so how close are two legal code words in Hamming distance? And so with these notions, it's very easy to come up with a criterion for when decoding is possible. So there are, in fact, a number of ways that are equivalent of stating it. Some are more complicated than others, and I have to introduce some of the more complicated ones because the quantum version is a straightforward generalization of the more complicated characterization. Yeah, but the first easy way, maybe I can ask you, yeah, maybe there's a very easy way, right? So we send one valid code word through the channel and then it gets corrupted up to L bits. So I stay within this Hamming weight ball of size L. And so now what is the condition on the distance so that I can uniquely decode? Maybe I can get the chat window up again. Yeah, all right. Any ideas, anybody?
If you want to answer, just type in the chat.
Mm-hmm. Yeah, so I can decode if no two code words are compatible with the corrupted bit string I receive. Okay, let me give it away.
There was an answer.
All right.
So someone says the distance larger than 2L.
Yeah, that's exactly right. That's right. Yeah, so the unit ball size is here, and so if the distance is larger than 2L, then there's no way that you can start with, yeah, that if you receive an single here, there is no ambiguity about where it came from. Yeah, there is always at most one code word that is distance L away. Okay, so distance being larger than or equal to, or actually strictly larger than 2L. Yeah, that is the easy characterization. Right, there is a trivial reformulation which we'll also use in the quantum case. Namely, we want to say that for all valid code words and for all errors in EL, if I look at the error acting on the code word, then I get back either the code word itself or something that is not a valid code word. Yeah, so no error can turn a valid code word into another valid code word. And this has to be true for 2L actually, to avoid ambiguity. Good. Fine, so I guess it's obvious that this is the same, just stated a bit more complicated, in a bit more complicated way. And now I'm going to write out an even more complicated characterization, which is going to be the basis of our quantum generalization. And what I want to do is I want to give meaning to this picture here. I want to introduce a fancy set of coordinates, if you want, on the space of all bit strings. Okay, and so the characterization is this. There is an invertible map L, yeah, that goes from the space of all n bit strings of length L to the following space, namely F2 to the K, and that's going to be the code. Cartesian product, the Hamming weight ball of size D, and then union some R, some set rest. So what do I mean by this? So the interpretation is that every bit string I can parameterize by saying, okay, I start at an element of the code. So in my color coding in this picture, this is denoted in green. Yeah. And then around every code word, I put a Hamming weight ball. Hamming ball. Right. So these are the bit strings that are the distance d away from a legal code word. And then there might be some other points left in the space that I haven't, that are not of Hamming distance d close to a legal code word. So let's call this the rest. And in our discussion, we can usually ignore the rest because we start with a valid code word and we assume that not too big an error ever acts on it. Yeah. Okay, so let's say we can have such a formulation, and now we want to constrain the way in which errors can act in these coordinates, where I again label my points by what is the closest code word and what is an offset within the unit ball. Right? So such that let's call it B naught in the unit ball, and this B naught should correspond to the center, such that if I take an error operator and I express it in these coordinates and I let it act on a code word that is undisturbed, yeah, so B naught is the center of the ball, so that means no disturbance, then the effect of the error is to just change the point in the unit ball, but not change the code word. Yeah. So okay. So all I'm saying is every point in n qubit space, in n bit space that is close to a legal code word will be mapped to something that is close to legal code word, the same legal code word by an error. Yeah. Okay. And now, if you have some mathematical training, then you will agree with me that condition number 4 is equivalent to condition number 2, but you would also insist that condition number 2 is much easier to understand. So why would anybody formulate it in such a complicated way? But of course, the goal is to have a quantum generalization. Good. I have some extra comments, which I leave up here on the board. You can access the board through a link provided in the abstract. But for now, I want to leave it here. And I want to move on to quantum coding unless there are any further questions or comments or anything.
So there was a question by Elena, I think, previously. So Elena, do you want to ask that again?
Yeah, I was just asking whether the operator E is a linear operator on the vector space.
At this point, not necessarily, but they will become linear in the quantum case. Mm-hmm. Right. Yeah, no, good question. They could be linear because I imposed the linear structure on the bit strings, but I don't assume that they're linear here. Okay. Good, but thanks for bringing up for asking this question, because we now have to explain what errors are in the quantum setting, and there they will indeed be linear maps. Okay, good. So now, right, let's start here. So as you have been exposed to in the previous tutorial, it is true that states of n qubits, of n quantum bits, are described by tensors psi, which are elements of C2 to the tensor n. And I promised before I will not use any physics in my talk, or I will not require you to know any physics, and I will not actually explain what I mean by this. Yeah, so if you already learned it from Thomas, then thank you, Thomas, that's great. But I will not actually define which way such a tensor defines a state or what a state even is. For now, it's just a formal construction that was going to be analogous to the classical coding problem. Right, now we know what is the generalization of a bit string, namely a tensor. Very good. So now we need to understand what is the generalization of an error operator. And errors will just, as you anticipated, Adina, will just be linear maps E from this tensor product space back to itself. But now, before we required that errors are local, that they only affect L bits at the same time. And now I have to explain to you what does this mean in this tensor language. Okay, and right, and so then I have to tell you that every tensor factor corresponds to 1 qubit. And an error that only affects a subset of qubits is a linear map that only acts on a subset of factors. Yeah, and if you have something that only acts on a small number of factors, you can extend it. So let's say you have an error that only acts on C2 to the tensor K and map that to itself. Then you can extend it by padding with identities. So you can look at this linear map, tensor identity to the n minus k. Yeah, and now you have obtained a map from the big n qubit space to itself. Yeah, in this way, you can always take operations that act on a small number of tensor factors and embed it into the bigger space. In this graphical language that many people like Thomas are using, it would look like this. So an n qubit object is a tensor with n legs, 1 to n here. And if I have padding with identity means I take the linear map E and I contract it with k of the indices. They are contiguous here, but they don't need to be, and I leave the other indices alone. Right? So this way I have explained what I mean by a linear map that only affects a small subset of all the tensor factors. Right? And this will be our error. So let's give a name to the space. And again, we will use the symbol EL. So let EL be the vector space of linear maps from C2 to the tensor n to C2 to the tensor n that act non-trivially only on up to L factors. Yeah, and by non-trivially, I mean different from just applying the identity. Okay, I hope that's clear. If not, this would be a very good time to interrupt me. Good, now I can define what the quantum coding problem is. So the message is now no longer a k-bit string, but I start with a tensor in C2 to the tensor k. And now I embed it, I encode it, and encoding means I have some linear map that takes psi to some phi, which now lives in C2 to the tensor n. And just as in the classical case, I've now added some redundancy maybe. Yeah, n is bigger than k. Then in the channel, again, there will be some error map acting on it, some E that might change L of the, act on L of the indices. And this is the corrupted tensor I'm getting. And now what I would like to do is I want to have some linear decoding operation that from this corrupted tensor recovers the uncorrupted tensor. Okay, so that is the basic task. And right. Now, we talked about codes before, and now I have to tell you how this notion of a code looks like in a quantum setting. All right, so a quantum error correction code, QECC, a quantum error correction code described with the parameters n, k, and d is what? It is a 2 to the k dimensional subspace C of C2 to the tensor n. Right? 2 to the k dimension means I can embed C2 to the tensor k into that subspace, and this embedded subspace that's going to be our code space, it lives in this big tensor product space, just as the short, the code words for k bit messages live in n bit messages. Okay, so now I need to define what I mean that this is a good code that allows me to correct for local errors. And for this, I will write down a condition, if I switch back, that will generalize this complicated condition we have here. Yeah, that's unfortunately the right way of expressing what a quantum code is. And I will give you the full definition so that you have seen it. But also, if you think it's a bit too much, I will give you a simpler necessary condition for a quantum code, and you will not lose too much if you fail to understand what I do next, but only understand what the simplified condition I'll give later. All right, okay. So what I want to do is I want to again have the same kind of coordinates on my tensor product space. So I want to have a linear map L that takes the space of all encoded, of where the encoded message lives in, and it expresses it as the code space as before in the classical case. And now no longer we have the Cartesian product, but the tensor product. And B is the analog of the unit ball. It's where the errors act, just that in quantum coding, one doesn't usually call it a ball, but one calls it the bad space. But since both start with a B, no damage has been done. And there might be some, dimensions of this big linear space that do not get used in this construction as in the classical case. This could be the rest. Okay, so I want to decompose the space in such a way. Also, I need an element just as before in B that tells me that no error has occurred, such that for all errors in ED, I get the following. If I express the action of the error in this representation of the tensor product space, and if this acts on some encoded message phi, tensor the origin of the bad space, so no error has occurred, then the error again just acts on the second factor, on the bad space, BE. Okay, so that is the quantum error correction condition. I can switch back so that you can compare, and it's really just the same as I had before. Now, some people who know about quantum coding, like Thomas, I don't know, they will say, oh, David, that is not, if you open Nielsen and Chung, that's not what the quantum error correction condition looks like. To which I would say, yes, Thomas, that is right. But the reason is that if you look very carefully, I have not used any scalar products and any metric information in that definition. And so I had the great pleasure before of discussing tensor problems with the likes of, let's say, Joseph Landsberg. And Joseph is a very patient person, but whenever I introduced a scalar product in a context where it wasn't essentially needed, he got very uneasy. And so I reformulated the usual quantum error correction condition in a way that I can state what it is, just as a tensor problem without any Hilbert space metric. Okay, so that's why I slightly changed it. Good. So if you can,
there is a question I think in the chat. I think it's good to ask at this moment. So someone was wondering that why the code space is a vector space.
Yeah,
has to be a vector space.
It is indeed a vector space. So it is the space of all the linear maps that act non-trivially on L factors. And because errors are, they are linear maps, and so the set of all linear maps is a vector space itself. And and if you take and those that have a decomposition like this, you can take the linear span, and so you get an entire vector space of error operators. This will become important a bit later. Yeah, it's a structure that is not there in the classical case, but that is here in the quantum case, and that will become important. So indeed, it is a vector space. Yeah.
Okay, so I guess you'll explain more the reason later. I think the question is more asking about why that's the design choice.
Right. For now, it is one, right? It just take the linear span of those. Yeah, I take right. Yeah, I think it will become clearer later. Mm-hmm. Good. Any other question? So I conceded up front that this might be, a bit heavy to digest. I mean, it's not difficult per se, but it's, involving all these such that for all quantifiers, existence quantifiers, blah, blah, blah. So I will give you a necessary condition for a quantum code that is easier to wrap your head around if you've never heard about any of this. And this is going to be the quantum analog of our third condition, namely for all messages in the code space and for all errors in ED, if I have such an error operator acting on a valid code word, then I get back either the code word up to a scalar or something that is not an element of the code. Yeah. So right, so again, we don't want errors to map valid code words into valid code words. And so if you are more from the algebraic geometry side of things and you don't, have never heard about physics at all, this is, I think, a good way of thinking about the problem. So a necessary task of finding quantum codes, not sufficient, but I think it captures, some of the difficulty of the problem is find a subspace of tensors such that no two elements are connected by a localized linear map, where localized linear map, I mean linear map that only acts on few tensor factors at the same time. Yeah, and so that's now a pure math question. I can hand out as a brain teaser. No, find big vector spaces in big tensor products of tensors that can't be related. Yeah, where no two elements of a space can be related by acting on a few indices only. Good. So this is the point now. Is there a message? Oh no, two participants raised
there. Two questions. Thomas first.
Yeah, I was just wondering. So, I mean, the usual choice is, as you have described, that the error operators are constrained to, let's say, n, or was it n sites?
L. I used L. Yeah. Mm-hmm.
L. Yeah. Couldn't it? So, are you always screwed if you allow the error operators to act globally? I mean, couldn't there be global operators that are physically relevant, but that they can still correct, right?
Yeah. You can, right, that's right. So it's a choice I can make classically or quantum mechanically. So I have to somehow restrict the set of errors. I can't, of course, if somebody eats up my message X in transit and replace it by something random, then there's nothing I can do. And I have to somehow restrict it. And a very natural way of restricting it is by having this locality constraint, but it's not the only one. In fact, the theory is quite, if you do it in the general way, it's quite agnostic about how you restrict the error set. It just needs to be small compared to all possible things that can happen. Yeah, just for concreteness, that I chose locality. Yeah, okay. No, it's a good question. Mm-hmm. And there's another raised hand.
Yeah, I wanted to ask, in the usual code word discrete setting, I mean, there are counting arguments to suggest there are choices possible for code words. In this quantum formulation, is there a counting argument to suggest there are plenty choices for code words in this tensorial setup?
Yeah. So there is, for example, an analog of random coding. So the way you prove the existence of good codes classically, like since Shannon and for many years after Shannon, nobody could write out a concrete code, but they just relied on randomized constructions. And there is a random coding construction also for quantum systems, and they also give you good codes with high probability. So these counting arguments sometimes carry over. And they use the stabilizer formalism actually to be carried over, and maybe I'll comment on this later. So if you remind me, once I've introduced the stabilizer formalism, I can tell you how to randomize to use basically counting, probabilistic arguments, which are just counting arguments really, to show the existence of good codes. Yeah. I think it's in part of one of my comments that I didn't read out here. Yeah, so randomly chosen subspaces have good distance with high probability, blah, blah, blah. Yeah, it's very good. It's a very good question. And it's a very, big and active and exciting field. And I could spend a lot of time talking about it, but I want to give you just, a brief overview here. Good.
Okay, I also have a question for the definition of the quantum error correcting code here. So does your definition actually include the quantum erasure channel, or needs something slightly different?
Wait. The channel is a channel, but I'm not talking about...
No, the erasure error, like we just lost the qubit.
Okay, so I mean, the quantum error correction condition is a condition on the code. It doesn't, it doesn't yet tell you, right, it doesn't tell you which channels can be covered. I guess it's kind of connected to Thomas's question. But certainly what we can see is we will find codes that correct against, let's say, arbitrary errors on a given number of qubits, and you could also throw them away, for example. In quantum erasure, I guess you know which one was thrown away, so that's extra information. So it's actually easier than the condition we're looking at here. So yeah, that's also included.
I see. So it depends on what is the calligraphic epsilon d, I guess.
It depends on what the calligraphic epsilon d, I guess. Yeah, that's right. And that is the basically Thomas's question that I've just chosen, you know, the most common example, namely errors that are localized, but you don't know where they have acted. And in erasure, I think you know which one has been lost. So it's extra information, so it's actually easier. So if we can correct against an arbitrary loss of information on any qubit, then certainly we can correct a loss of one qubit if we also know which one got lost, which one we've lost. Yeah.
There was also a quick clarification notation question. So here it's a calligraphic ED, but I think earlier we used EL. So is there a difference?
Yeah, the D and L are okay. So D I used for the two letters appear here. No, D are used for the distance of the code. So D is a property of the code, and L is a property of the transmission channel. Yeah, so L is how many bits get corrupted by the channel, and D is what is the distance of the code. And if they have this relation classically, then I can correct. So that's why the two letters are both relevant. Okay, good. Any more questions? Why do we take E in cal ED and not in equation 4Q? Right, in 4Q, because the definition here is, wait, where am I now? I mean, classical here.
No, I think that was the question I asked.
That was the question.
The definition of the quantum error correction
code. So because we wanted to define what an NKD quantum error correction code is, that then corrects up to, correct channels that introduce L errors as long as L is more than or equal to D. Okay, good, right. Good, so now, now we have this is now an algebraic geometry question. So is that easy, is it difficult? Yeah, I don't know. Here I've given you an example. I don't want to discuss it. I just, I just presented here. We're going to discuss it later in the stabilizer picture, but just maybe that you get a feeling for it. So this here is a basis of a D equal to 1, N equal to 5, K equal to 1 code. So D equal to 1 means it can correct any error on 1 qubit. Yeah, it encodes into 5 qubits and it encodes 1 qubit into 5. So K equal to 1 means I have it's two-dimensional, so that's the basis. And N equal to 5 means, I live in this 5-fold tensor product. And this is, of course, this quantum information notation for tensors, where I write 1, 1, 0, 1, 1, 0 to mean this tensor here as an element of C2 to the tensor 5. And I now claim that, that no two elements of the linear space spanned by these two vectors can be mapped onto each other by a map that only acts on one factor at a time. Okay, maybe not. It's unclear how you would see it if you look at the direct representation of these tensors. But I would give you now an indirect way of reasoning about those using simple matrix groups, which will make it quite plain why this is true. And more importantly, for such a simple example, you could probably check it manually by just fiddling around with the symbols and plugging in the definitions. But the technique that I will introduce next has the advantage of scaling to very big spaces. And it's also the language in which, for example, this toric code, this topological stuff is formulated. Good, right. So this was the preparation. Now comes the actual main part. So I need your attention now for the next 10 minutes, because now come the important definitions. Everybody ready?
Okay, maybe before switch to Pauli groups. And so the question, is there an easy certificate for a given code?
Is there an easy certificate whether a code has a given distance? No, that's, is there a certificate that a code has a given distance? I don't believe so, no. So it's a subtle question. So it's certainly NP hard again. If you give me a code to decide what the distance is, but now of course NP hard is compatible with there being a short certificate, but even that I don't think exists. I would be surprised. So these are difficult questions. So in general, again, people use these random coding arguments that they can come up with a random construction and then they know with high probability it's correct, but they can't actually prove it in that given instance. So I don't think, I'm not sure whether there is a certificate, but I don't even think that is the case. So we need, be a bit smarter, and that's what we're going to do in the second part of my talk. Use some smart constructions where we can actually prove things. It's a very good question. All right, good. So now how do we construct quantum error correction codes? And it's a fact that almost all known quantum error correcting codes arise as the joint eigenspaces of certain matrix groups. So let me write those down. They're very elementary. It's very easy. It's just these easy things you have to remember. So the big player here are the famous Pauli matrices, which are just 2x2 matrices that most people who have to do anything with math or physics come across sooner or later in their lives. And so let me define the Z matrix and the X matrix. Yeah, so these are basically, these are all we need. And I'll just introduce a few more definitions, namely, but they all arise from Z and X. So Y is defined to be negative I times the product of Z and X. And if you work it out and you get all the faces right, then you find that this is, this is this matrix with imaginary units plus minus on the off diagonal. And we also will need the identity, 2x2 identity matrix. Yeah. So these things, of course, they appear everywhere in the representation of quaternions or the representation theory of SU2 or whatnot. You know, quantum mechanical description of spin. You've probably seen them before. Yeah. Let's introduce more notation. This one we call sigma 3 because Z is the third coordinate, X is the first coordinate, so that's sigma 1. Y is also called sigma 2. And the identity we call sigma 0. So now we have 4 matrices, sigma 0 to sigma 3. Okay, some elementary properties. First of all, if I take the square of any of these matrices, I get the identity. Yeah, it's obvious here. If I square that, I get the identity. If I square this, it's a flip. If I flip twice, I've done nothing. It's the identity. It's also true for Y, as you can check. So they square to identity. So that's going to be important. And also, if I take two non-trivial Paulis, then they will anti-commute. Yeah, so Z times X is minus X times Z. And Z times Y is minus Y times Z, and X times Y is minus Y times X. So they anti-commute. Right, okay, by this I mean all non-trivial pairs anti-commute, but I think this is obvious. Good, fine. So now good, you've already understood the first part of the construction. Now let's make it a bit more interesting. Okay, so now we are interested not just in 2x2 matrices, but in tensor products, of course. This is a workshop about tensors. So let's define the n-qubit Pauli group to be the following set, which I promise you is a matrix group. And you just take a Pauli on every tensor factor and you tensor them together. Sigma I1 tensor, sigma I2 tensor, and up to n times, sigma IN. Yeah, so these you tensor together. And then if you want this to be closed as a group, you also have to add faces plus minus 1 and plus minus imaginary unit times these tensor product of Pauli matrices. And then you can work out that this is a group where the I1 to IN are 0 to 3. Okay. Right, so that's the Pauli group. That's going to be the central object that we'll be working with. And these things are called Pauli operators in physics. And these we'll refer to as phase factors. Okay. Good. So far, so trivial. I've never said it would be difficult. Now, right, let's record a few properties of the Pauli operators. And in fact, I think I need only 2, so it's very easy. Okay, so if P is a Pauli operator, so it's one of these things without any faces, then again, it squares to unity. P squared is the identity. Yeah, now it's the identity on a 2 to the n dimensional space. Yeah, and that's obvious because if you take the product of a tensor product of matrices with another tensor product of matrices, you get the tensor product of the products. But the individual Paulis, they square to identity. So you just get identity, tensor identity, tensor identity. So in particular, the eigenvalues, that's going to be important. The eigenvalues of P are going to be plus minus 1. Yeah, because it squares to identity. And here's the second property we'll need, namely, I will have to be able to compute the trace of a Pauli operator, but that's also very simple because the trace of a tensor product is just the product of the traces. So it's the product from I ranging from 1 to n of trace sigma, well, maybe j, sigma ij. And now, what is that? What is the trace of Paulis? Well, let's go up. So So the trace is 0 here, it's 0 here, it's 0 here, and it's 2 here. Yeah, so the trace is 0 unless we hit the identity, in which case the trace is 2. Right, so what do we have here? So we have...
Question?
Yeah, delta...
Why do these things have to square to be identity and not plus or minus identity?
Very good question.
Oh, great to see you, by the way.
Sorry?
This is Joseph. Great to see you.
Yeah, I recognize your voice. Good to hear from you. So, right. Yep. So sorry, maybe my language was not so super clear. So by convention, a Pauli operator is just one of these tensor products without any phase factors. So when I say a Pauli operator, I mean just one of these things here. And I distinguish that from an element of the n-qubit Pauli group. So you might say it's not a very good nomenclature to say an element of the Pauli group and a Pauli operator. These are different objects, but that's a convention. Yeah. And so because there is no factors of I involved here, they square to +1 and not to -1. Okay?
Okay, thanks.
Yeah, so basically by definition is the answer, right? Okay, so now if I compute the trace, then I will get, either if all the indices are 0, so if I just have the identity, I will get 2 to the n, yeah, because I get 2 n times the product of this, or else I get 0 because there's going to be 1 0 along the way. Right, and so again, how do I interpret this? This means, okay, I've seen the eigenvalues are ±1, but the trace is 0. So that means that half the eigenvalues are positive and half the ones are negative. So the ±1 eigenspaces have a dimension 2 to the n minus 1 each. Yeah, unless we fit the identity. Right, and so this is already, a quarter of the way to a stabilizer code, because now what I'm doing here is I'm taking these elements of the group and I'm looking at their eigenspaces, and these eigenspaces, they are going to form the quantum error correcting codes. Yeah, it's just we have to be a bit more subtle. Introduce one more ingredient. Okay, good. So now we are approaching the central construction. If I scroll ahead, here the central construction is about to come. But before I give the general central construction, I will make a preparation where I look at one more special case. And then for the mathematicians, you can now zoom out because it's all contained in the next definition. But for the non-mathematicians, maybe you need some easing into the problem. Okay, so up here, we looked at the eigenspaces of one Pauli operator. I will now look at the joint eigenspaces of two commuting Pauli operators. Yeah, that's the next step. So I take two Pauli operators, P and P prime. Yeah, and let's quickly think whether we can understand when do they commute. Yeah, but since every factor either commutes or anti-commute, then the two Paulis, they commute if and only if this distinct non-trivial Pauli matrices meet at an even number of factors. Yeah. So when I commute them past each other, every pair here will give me either a +1 or a -1 because they commute or anti-commute. And if I get an even number of negative ones, then I'm in business. Then I have two commuting Paulis. Yeah. There is this commutation relation has a nice geometric interpretation in terms of finite symplectic spaces, but I wanted to talk about it, but I'm afraid I will not have the time. So you can ask me if you want to know about this. Okay, so if I have now two commuting Paulis, then it means the space decomposes, the total vector space decomposes into up to 4 subspaces, namely, those are where the, if they commute, I can jointly diagonalize them, and I can look at I get then for the joint eigenspaces, I get eigenequations that p phi is plus or minus phi, and p prime phi is plus or minus phi. So I have 4 possible combinations: plus plus, plus minus, minus plus, or minus minus. Yeah, and in fact, it will turn out that each of these spaces has dimension 2 to the n minus 2. So now, before I divided my space into 2 subspaces, now I divide it into 4 eigenspaces of these two commuting Paulis. Okay, so let's look very briefly at an example, and then we then we do the general construction. Okay, so here's an example. I take n equal to 2, and the two Pauli operators I will be looking at are x tensor x and z tensor z, potentially with phase factors in front of those. X and z they commute because x and z anti-commute, but there's an even number of places where they meet. So they jointly commute. And now I will just look at the different signs. So let me look at the joint +1 eigenspace where S1 and S2 are both 0. I will now write out a tensor, and then we can check that it's indeed a joint eigenvector. And the tensor that does the job is very simple. It's this one. So I take the two unit vectors and I tensor them together, and I take I take the first unit vector, I tensor it with itself and add the second unit vector. So why is this indeed a +1 joint eigenvector? Well, let's check the ZZ first. Z multiplies the second index, the second coordinate by -1, but that means I get a factor of +1 here times a factor of +1 here, and here I get minus times minus, and they multiply to plus, right? So indeed, Z tensor Z maps this tensor to itself, and X tensor X, well, it just exchanges the two summands, because X is just exchanges the two basis vectors, right? And if I exchange the two summands, obviously I get back the same tensor. Right, okay, and by the same argument, by the way, I get, if I change the sign here, I get the minus, -1 + 1 eigenvector, joint eigenvector. Because again, XX interchanges the two factors, and in this case, I get, if I interchange the two factors, I get the negative sign that I need here. And okay, I give one more example. There's only two more. Should I write them all out? I leave it at this, right? And then you can, I give you this one for the physicists. 1, 1 happens to be 0, 1 tensor 1, 0 minus 0, 1 tensor 1, 0. To the physicist, what is the name of this vector in physics? I will go on with the lecture, and I wait for somebody to unmute themselves and reveal it. But so what we have done is indeed, so the claim was that all these eigenspaces that we have, they have equal size, I mean 2 to the n minus 2. In this case, n equals to is 2. So we have 4 eigenspaces of dimension 1, and this is in fact true. We found one eigenvector for every combination of eigenvalues. Good. Okay, so now you are all officially well prepared, and it's good because I'm running out of time, so I should get going here. And I can now tell you how to use the Pauli group in general to construct spaces that will turn out to have good quantum error correction properties. Okay, so here's the construction. There's 3 steps. So first we choose K commuting Pauli operators. G1 to GK from the n-qubit Pauli group. Then we choose a bit string S in F2 to the K, and that's going to label the phases, the signs of the joint eigenvalue equation. And we define now a subgroup. We define S to be the matrix group generated by -1 to the S1 G1 to -1 to the SK GK. So I take the commuting Pauli operators, I choose a phase of ±1 for each, and they generate a group, and that's the group I want to work with. Okay, so let's look at this group S. So first, there is a claim that S is smaller than or equal to 2 to the K. That's very easy to see. Let me sketch why this is true. And this is because, basically it's because all the generators here, they commute, right? So that means if I take an arbitrary product of terms of this, I can always order it in such a way that all the G1 generators come first, and then we have all the G2 terms, and then we have all the G3 terms, and so on. So an element of S is of the form, right, -1 to the S1 G1 times some power X1 times -1 to the S2 G2 times some power X2, and so on. But again, these things square to 1. So in fact, I can restrict X1 to be an element of either 0 or 1, because if it's 2, then it wraps around, and so on. So I have K powers, which can either be 0 or 1. So I have at most 2K elements in this group. Okay, I wanted to give an example, but maybe I leave it at this because I want to get a bit further in the lecture. Right, so now we are interested in the case where this bound is equal. Yeah, so there are no additional relations among these generators than the one we've already given. And this is the case that is central to our construction. Okay, so if indeed the group has cardinality 2 to the k, then we call the generators independent, and S is called a stabilizer group. And the joint +1 eigenspace of all these elements of the group, this is a stabilizer code. So these are the subspaces we're going to work with. Okay, it's very easy, yeah? Just the generalization of what we had before in the 2x2, in the n equal to 2 case. I realized that no physicist had told me what is the name of this vector here. I'm mildly disappointed as somebody who's about to teach quantum mechanics 1 in the summer term.
There is an answer in the chat, though.
Oh, there's the answer in the chat.
Yeah.
It's the singlet. Very good. Very good. Singlet. Yeah, you would have passed quantum mechanics 1. Excellent. I'm very happy. Okay, good.
Oh, also a quick question. So someone was asking about terminology. So why is this called stabilizer?
Stabilizer, because I'm looking at the joint +1 eigenspace. So in other words, C is the set of phi in C2 to the tensor n, such that G phi is equal to phi. So phi is stabilized by G for all G in S. Yeah, it refers to this +1 eigenvalue condition. That we say G stabilizes phi. Yeah, that's the reason. Good. A few quick facts about this group, and this is maybe the last part where I need your very close attention. Yeah, if you understood this, then we are basically done. All right, here are some facts. So first, if I have the group and I want to project, and I want to get the joint +1 eigenspace, what can I do? I don't know, I can run MATLAB or whatever to find a joint diagonalization, but there's a more elegant way, namely, if I just take the average of all elements in the group, then this you can easily compute, that's true for every matrix group, is the projection onto the joint +1 eigenspace of all the elements of the group. Yeah, so this projects onto CS, so this is a way of explicitly getting the space from the group. Yeah, I don't give a proof because it's a standard property of matrix groups. So then the next statement is more interesting, namely the dimension of each stabilizer code is 2 to the n minus k. Yeah, and this I can quickly show you how to see. Right, so you use the formula in 1, and the dimension you get by taking the trace of the projection operator. So you compute trace S. Yeah, and what is it? It's 1 on the cardinality of S, which is just 2 to the minus k by definition of a stabilizer group. Yeah, and now we have the sum over all elements in the stabilizer group, the trace of the element. But we've seen before that this is 0 unless G is the identity, in which case we get 2 to the n. So that is delta G identity times 2 to the n. And so we get 2 to the n minus k as claimed. So that was easy. Yeah. So now, right, that was my claim before, that all these joint eigenspaces have the same size, right? And that is true. And there is a next important statement, which is just trivial linear algebra. Namely, if I take two stabilizer groups that have the same generators, but differ in the choice of phases, then the resulting codes will be orthogonal to each other. And that is just the statement that if I have a Hermitian operator, then the eigenspaces belonging to two different eigenvalues, they are orthogonal to each other. Yeah? And if I take the same matrices here, and by choosing a different S, I just choose the eigenspaces, so I get orthogonal eigenspaces. But now we are at a big point in this development. Yeah. Now let's count how many choices there are for the faces. Well, there's 2 to the k choices for the S's because I have for every generator I can choose +1 or -1, right? And so this means now, and now comes the important point. This you have to understand, and then I'm happy with you, right? So I take this big tensor product space, and it now decomposes into a direct sum, where the summands are labeled by my choice of which eigenspace to look at, and the eigenspace is given again by one choice of phase per generator. And then I get a copy of this code, which depends on the choice of phases. So let's call it C of S or something. Yeah, and so because each space here has dimension 2 to the n minus k, yeah, and here I have dimension 2 to the n, and I have 2 to the k summands, I've actually found a complete decomposition. Yeah, and this is going to be important that I can decompose the entire space this way. And now I can, and this is now really the last time I need your attention, I can write this a bit differently. I can say, okay, so put differently, this means that our original tensor space has the structure of, is equivalent to a different tensor product. Namely, I take the code, yeah, and I have many copies of the code, and which copy I have is labeled by a bit string of length k. And so I have the following isomorphism. C tensor, let me write it out and then explain what I mean by this. So by this, I just mean the formal complex linear combinations of bit strings. Yeah, so this is the space, sum over S in F2 to the k, some complex coefficient and some unit vector, some formal unit vector indexed by a bit string. Yeah, and CS is a complex number. Yeah, and the way to read this is, in order to specify an element of this original space, I can specify here which copy I'm living in, and here where I am within this copy. Okay, and this decomposition is going to be the decomposition that appeared in the definition of quantum error correction. This is going to be where my code messages live, and if I'm lucky, all the errors will just label on these faces and just, move my code around in the vector space without changing the content of the code space itself. So that is what we're going to do next. Right. And that is it here. So we can move on to the final set of slides. I don't know, to the final page.
Maybe a good point for a question in the chat.
A very good point for questions. Yeah.
A lot of questions, so I will not read it out. You can probably read.
Wait, sorry, there is
from these properties, do you get the converse? That is, starting from G, you get a stabilizer code, is G the full automorphism group, blah, blah, blah. Did you see it, or should I continue reading?
Right, and wait, so, all right, okay, so you have the subspace and right, and the stabilizer group there's a unique correspondence between stabilizer code and abelian subgroups within the Pauli group. Of course, there's a bigger automorphism group if you allow for a bigger ambient group, but if you restrict to the n-qubit Paulis, then there's 1, 1. Yeah, and the connection is again in terms of finite symplectic geometry, and I'm desolate that I don't have the time to talk about it because that's my favorite topic in life, but I'm lacking the time here. Yeah, but yes.
Is that another short question on that you're talking about this complement space R before, so there is no R here?
Here at this point, there is no R. In fact, yes, I've in the best possible case, I can divide my space up cleanly into labels of code words and labels of errors. And in this case, this works here. And on our next page, it will at some point fail to work. But for now, yes, we are in a very good situation where R is actually empty. Mm-hmm.
And yet another question from Michael Lindsay.
Hi. So you mentioned before that the cardinality of S is at most 2K, but it looks like in the sketch of proof of your proof for item 2, you assume that it is 2 to the K?
Yeah, that's by definition. So maybe I should have been clearer. So I only consider those cases where there is equality. Yeah. So there is, we'll sometimes see that so it just basically means there is no further constraints, relations between my generators. We will sometimes see in the second part of my introduction, when we go to the toric code, that we do have relations and then we have to mod them out. But for now, to make our life easy, I just wanted to ignore the possibility of there being redundancy.
Okay, thanks.
So yeah, sorry, proof by definition. I just should have been more clear about my choice of words. Okay, so now things are getting, I have 9 minutes. Aha, okay, that's maybe just so possible. So how can we error correct now with these constructions? Okay, so here's the construction here. So we choose independent generators, G1 to GK, so they generate a stabilizer group. And then what we've seen before is that a tensor phi is an element of the associated code space if it's a joint plus one eigenvector. So if it satisfies all these k eigenvalue equations, yeah, it's being stabilized by all the generators. And now we choose some Pauli operator E, and I now use the letter E because the Pauli operator I'm looking at now will be interpreted as an error. And I analyze what happens to these eigenvalue equations up here when I evaluate them not for phi, but for E phi. Yeah, and now this is a calculation that many of you will have seen before. It occurs, for example, if you work with, I don't know, the weights of work out the weights of a Lie algebra and use the laddering trick, then you use the same calculation. So I want to understand what is the ith generator acting not on phi, but on the perturbed phi where the error has acted on it. Yeah, so then what I do is I just insert an identity here and reproduce the equation other than that. And then I put strategic parentheses. And what you see here is that we have a sandwich equation where we just have Pauli operators. But now I can commute E past the GI. This will give me a +1 or -1 because they either commute or anti-commute, and then it meets its inverse and gets annihilated. So this will just give me ± GI. Yeah, and so what is left is ± E GI phi, but phi is an eigenvector of GI, so we get ± E phi. Right, and now this is a very simple but extremely important observation, namely E phi is also a joint eigenvector, but it might have different eigenvalues. Ta-da! This is now where things get serious. So if E anti-commutes with at least one generator, then E phi lives again in a code space, but in one of the code space that is orthogonal to the original one. Okay. Good, so let's look at this in a bit more detail, and 7 minutes, all right. Okay, so what are the signs that appear in this construction? So if you fix an error and you see how it interacts with the generators, yeah, then there's gonna be a phase depending on the generator. And these phases here, this vector of phases, they are called the syndromes. The syndromes as of the error, and the terminology syndrome comes from classical error correction because there one gets similar bits that tell us which error has occurred. Yeah, and right, and so the new eigenvalue equation of the perturbed vector is now given here, and it's just the same as the old eigenvalue equation, except for we have all these syndromes here in front. Okay, good, fine. Any question here? Right, now I have an example and I have the conclusion and I have 6 minutes. So I will skip the example, which is anyway a bit easy to do. And now I will come to actually construct quantum error correction codes. Okay, so now I will do this for the easiest case of a distance equal to 1. Yeah, and then you already get the basic idea here. So I now write out a basis for the vector space E1, which you remember is the vector space of linear operators that act non-trivially on 0 or 1 qubit. Yeah, and here is the linear basis of it. So there is only one operator that acts on 0 qubits, which is the identity. And then we got 3 operators. Well, we got X, Y, and Z. They act on the first qubit, but they together form a basis for the space of operators on the first qubit. So in fact, every operator, every linear map that acts on the first qubit is a span of these 4 terms. Yeah, so we have a basis here. Yeah, and so then I need all the parties that just act on the second qubit and so on. And so I get in total, I get 3n non-trivial ones because it's n qubits and I have 3 choices, X, Y, or Z for each one. And then I get the identity on top of it. Yeah. So these are from a basis of the space E1. And fortunately, this basis falls within our group theoretical framework. So we can use our group language to analyze errors. So that's fantastic. Okay, so now comes an assumption that we need. So now assume we've chosen our stabilizer group with good foresight and in a good way. And we use, for example, the toric code later to see how this works. So now assume that our generators are such that each of the 3n plus 1 EJs, so the 3n plus 1 basis elements up here, has a unique sign pattern Sj. Yeah. So the sign pattern is again given here, right? And we want that each element of this particular basis induces a different sign pattern. So each element is associated with a different joint eigenspace. Yeah. Then we have a well-defined linear map from the following information, namely the code tensor, the sign vector, the vector of signs, C2 to the k, into the big space, C2 to the tensor n, such that if I take an element of the code and the sign pattern given by the jth, induced by the jth error operator, this I just map to the jth error operator acting on phi. Yeah. So that's it. Yeah, this is an invertible linear map. Why? Because all the different EJ will map phi to a different orthogonal joint eigenspace. Yeah, because all the sign patterns are unique and every sign pattern labels one joint eigenspace. And this map is just the inverse of the L map that we needed before in the definition of the quantum error correction condition. And so we are done. That's it. Yeah. And we are done. And I said before that this quantum error correction condition is not difficult, but maybe a bit counterintuitive. So let's look at an easier. I haven't actually written it out. Okay, I wanted to include one more step here because we are done for basis, and I wanted to show you that once we're done for basis, we're done for the entire space. So let's actually do this calculation. All right, okay, so and then it gives me some, some occasion to talk a bit more about it so that you actually understand what's happening. Now I take a general error that is a linear combination of stuff acting individually on one qubit alone. Yeah, a linear combination of this, right? And so I want to see how E acts on. Right. Okay. So let me write it again out in this transform picture. So I want to see how it acts on phi tensor E0. Yeah, phi tensor E0. This just means phi is an element of the code space, and E0 means I have all the signs are equal to 0. Yeah. And now, of course, what the error does is by linearity, what the jth term is doing, it's just changing the label of the space I'm living in, right? Because the EJ error just puts me into the eigenspace labeled by its unique sign pattern. Yeah, and so this will just give me by linearity phi tensor sum on j, Cj, and then the sign pattern of the jth error. So now I'm done. Yeah, this is the quantum error correction condition. Yeah, and so maybe if this was too algebraic, let me again go back to the high level. So what I'm saying here is that for every element of a basis of the space of single qubit errors, it will take my code and map it to an orthogonal copy of the code, but it will not mess with the code itself. It will not map a valid code word to another valid code word. Yeah, this was the other condition I said before. It might be sufficient to understand what's happening here. Yeah, and so the good thing that happened now is that if I want to verify that I have a quantum error correction code, I only have to solve a combinatorial problem. I just have to see whether for a given set of generators, all these error operators induce a unique sign pattern. Okay, and now if you give me 1 more minute, we can outline how to do it for this horrible n5k equal to 1, d equal to 1 code that we looked at before. So instead of with this vector representation of the space of tensors, people would usually in quantum information just give the generators. Here are the generators. And in this notation, the tensor symbols are implied. Yeah. So these are tensor products of Pauli's on 1, 2, 3, 4, 5 qubits. Yeah. And now I can check, you know, there is how many, for 5 qubits, I have 3 times 5 plus 1 is 16 possible errors. So there's only 16 sign patterns I have to check. So I can, in this case, I can just do it manually. So let's do it maybe for 1 or 2 and then, you know, prove by improper induction. So let's say that the E operator equals, let's say, the Z operator on the first qubit. Yeah, so then it anti-commutes with G1, so I get a -1 here. It commutes with identity, I get a plus. It anti-commutes here, I get a minus, and it commutes with Z, so I get a plus. Yeah, and let's say, let's test another one. Let's say I had, I don't know, X acting on the last qubit, then I get +1 X and X commute, +1 X and Z anti-commute, -1 X and Z anti-commute, -1. So far we've tested 2 out of 16 and we've gotten 2 distinct sign patterns. So it looks like maybe this could work. And indeed, you can just check all the 16 possibilities and you get a unique sign pattern. And then by the general theory, we have constructed a quantum error correction code. So we have constructed a subspace here with the property that no 2 elements of that subspace can be connected to each other by acting on one index, and in fact not even by a linear combination of operations acting on one index each, which is a stronger condition, and we have also proved this. So here's a summary of my first part. So we have constructed spaces of tensors as joint eigenvectors of commuting Paulis, and the quantum error correction condition now reduces to a combinatorial problem involving the generators. So we come from a tensor problem, which is usually unsolvable, to a combinatorial problem, which is usually just horrible. So from hopeless to bad, we've improved. But bad is still pretty bad. Now here there were only 16 conditions to check, but in general, if n is big and d is big, there's exponentially many in n and d conditions to check, so we can't do this. But yeah, there are some smart constructions, in particular this toric code construction I want to tell you about next week, I guess, for how to derive good quantum codes without running into combinatorial explosions. Okay, and I've used up my time.